So I'm a PhD student in Vienna, and I'm also employed at SBA Research. And I did multiple things, including was founding member of several hacker spaces in Vienna. And what I want to talk about today is, since we had this last talk and we were talking about different authentication methods for iOS, Google, and mobile Windows Phone, and there are so many of these operating systems. So we looked at this at an operating system agnostic way, and how can we augment a primary authentication system just with the mobile phone itself? So there are two main spaces in Vienna. One is MetaLab, the other one is HappyLab. MetaLab is more of the living room for nerds style hackerspace. HappyLab is more of the shop style service oriented FabLab space in Vienna. And both come with laboratories where there are all kinds of machinery for people to work on their projects. And so we have like vinyl cutters, which is great for making t-shirts. We have laser cutters where you can cut wood and acryl and engrave aluminum and glass and all kinds of digital production things. There is an electronics lab also there, and there are, of course, 3D printers. And some of the two spaces have different concepts. Some machines are free, some machines you need to pay for, so there is kind of accounting in the back end. Some machines are so heavily demanded that you need a reservation for a certain time slot. But most of the machines are quite fragile and expensive, so you need special training to operate them, and you need to follow safety rules. So we had the problem that an unsupervised laser cutters caught fire at HappyLab in Vienna, for example. So no usage of these machines without proper introduction, and you need to stay close to the machine. So there are different methods in HappyLab. There are RFID cards to enter the laboratory and also to use the machines. At MetaLab, there are eye buttons used for this same purpose. However, of course, people cheat. People swap cards, people trade machine time. People do not follow safety regulations, leave the machines locked on, maybe by accident, maybe because it's already so late and they need to catch up the last train. Things like this happen, so it's not always malicious intent. And of course, people go away maybe just briefly to the toilet while they actually should monitor the machine if it's working as intended. And these are the kind of situations where GUI inactiveness does not translate in actual inactivity of the user, because people need to load or unload, adjust the machine, things like this. So it's not like you can solve this just with a 3-minute timer and then you lock out the people from the machine. So we wanted to somehow improve the system, and we're looking at different ways and exploring different things. And it would be nice to somehow not to have another token. Maybe we can use somehow the mobile phone. And mobile phone would have many different advantages. So basically, it's so if we take the UDS framework from Bonneau et al., we can our system would fit into 7 and half of the 8 points that the Bono system offers for this kind of authentication systems. It's physically effortless. You don't need anything to do to get it working. It's quasi nothing to care. This means, a nothing to care system would mean you have no additional artifact, you have no artifact at all. A quasi nothing to care system, which is an exception in the UDS framework, is no additional artifact you need to care. It's nothing. It's memory-wise effortless. It scales well. There's no changes regardless how many users are using it. It's easy to learn. It's efficient to use. Infrequent errors. All these points. But with mobile phones, including mobile phones, we hope they are too personal to share. But on the other hand, you need to support a lot of operating systems. So yes, of course, the two major operating systems have over 90% of market share, but there is a very long tail on mobile phone operating systems. And of course, you have a lot of versions to maintain. So can we use the mobile phone somehow in a way to augment the system without any additional app, just maybe by its presence? So let's look at a modern smartphone. What kind of transmitters do they come with? So of course, there is the mobile network transmitter. However, it's quite complicated in the sense that you have today you have 3 different network generations, which all work on different frequencies with different modulations. A mobile phone can be attached to multiple cells in your area, and they all use a pseudonym mobile subscriber identity in some form. This means that they're not broadcasting their unique ID over the air. However, they use the TIMSI. And there are a few ways to de-anonymize the TIMSI, but they do not scale well in a large environment. So you have to listen to the cell, and if you know the phone number, you can call them and you can sieve out the TIMSI that is paged multiple times, things like this. Okay, let's look at the other transmitters. So for the mobile phones, you will probably end up with half a dozen receivers for all the different standards and frequency ranges. And it does not scale well. So the other transceivers you find on a mobile phone. There's RFID and NFC, which have a pretty short range. So you need to be more or less in contact with the machine. There's Bluetooth. Bluetooth has quite a complex discovery protocol. I will come back on this later. And there's Wi-Fi, which also has multiple states you have to care of, but it's offer a quite easy discovery mechanism to see if a device is in vicinity or not. So in the paper, we compared the different methods, and the 4 main points are availability, so how many devices supported, prevalence, how many devices usually have this transmitting function enabled, or at least the users use them on a regular basis. It's interesting that there are sometimes different numbers for iPhone and Android users. We also compare the range. We compare how fast you can enumerate or blind scan your vicinity to find all the devices, and how fast you can make a presence check. So just checking if a specific device is present. Oh, sorry, I skipped here. So we found, based on other studies, that Bluetooth, for example, is only enabled in about 1/3 of the device on a regular basis. However, Wi-Fi is enabled quite often on iPhone users 98% of the time, on Android users 89% of the time. So we took a closer look on Wi-Fi. Wi-Fi, you have to distinguish between if the phone is connected or not connected. And you probably already heard Wi-Fi can be used to track users based on the probe request. So there are different ways how a Wi-Fi device can find all the access points in vicinity. One is just to listen to all the channels one after each other, and to receive beacon frames which advertise all the access points. However, this takes quite a long time. So most mobile phone manufacturers choose another way, which are probe requests. So probe requests is a phone cycling through all the channels and sending a probe request on each of the channel, and all the access points answer to this probe request. This works much faster than scanning each Wi-Fi channel, because these beacon frames are usually only sent 10 times per second, and then multiplied with all the channels and interference, it can take quite a long time. So because some people were using this for tracking devices, Apple started with MAC randomization. This means that during probe requests, it does not use its real MAC address. It uses a randomly generated. However, it has been shown that this scheme is very weak. So on some devices, the MAC randomization uses the random MAC in the header, but in the option headers, they use the real MAC address. Also, they just keep increasing the sequence number, not resetting it between the different randomization steps. And also, it's only randomized when the phone is on sleep or when the screen is turned off and it's not connected. However, as soon as you turn on your screen, it uses its real MAC address. And because it's not resetting the sequence number, it's very easy to correlate the random MAC address with the real MAC address. So this is the disconnected state. In the connected state, so a phone is associated with the Wi-Fi. Most phones still send out probe requests, but less frequent. This is because you might get out of range of your currently associated access point, and then you need to know which other access points are in vicinity, and for roaming between access points. Also, most phones use one of the power saving schemes that are available on Wi-Fi, which basically means they do not listen all the time to the access point, but they poll the access point every few seconds. And then there is, of course, if you are associated, you have all the network traffic like broadcasting, ARP requests, DHCP. Your phone is downloading updates, connecting to one of the messages servers from the apps that you have installed on your phone. So you have constant traffic going on, and of course you have ARP and ICMP echo and all these things that the phone usually also supports. So so this is a table that sums it up for presence and enumeration possibilities on Wi-Fi. In the disconnected state, we just passively can sniff probe requests. In the connected state, we can passively monitor the traffic and just record the MAC addresses that are used. And if it should actually happen that within a time frame the phone produces no traffic whatsoever, then we can still actively probe for its existence, for example, using ICMP echo, but some devices do not answer on ping requests, but they have to answer on ARP requests or IPv6 neighbor solicitation requests. They cannot do without this. So this is like a small flow chart, what you have to do, depending on different devices. And if we should actually get to a point where we cannot, if you have MAC randomization, but we cannot de-anonymize it, then the simple solution is to ask the people with this phone just to connect to the Wi-Fi. Most users use the Wi-Fi anyway by default and auto-connect to the Wi-Fi because you get much faster data rates, and it does not account to your monthly limit. So with all this collecting of Wi-Fi data, there might be a problem because just collecting Wi-Fi data might be considered harmful, and Google learned it the hard way with the Google Street View cars that were collecting too much of Wi-Fi, and they had quite substantial fines to pay for that and had to delete all the data. So how can we collect Wi-Fi data in a privacy-preserving manner? Well, we came up with a scheme that uses Bloom filters. So we only extract the MAC address and we put them into a Bloom filter. The nice thing about Bloom filters is that you can only add things to it and you can test if the Bloom filter has seen the specific pattern before, but you cannot extract the patterns. And they have no false negatives. They might have a small false positive rate depending on how much you put into it and or how you design it. However, since you can only add new patterns, but you can never remove patterns, this means that we need something to expire MAC addresses that we have seen, because we want to know if there have been no activity from the phone like in the last 3 or 5 minutes. So we should consider that the user has left the lab. So we use a ring of Bloom filters, and we start a new Bloom filter every minute, for example. And every time we need to we do a presence check, we simply check in all of the Bloom filters, and after 5 minutes, we discard the oldest one. And here you can also see we can also, for the active probing requests, we can also use the DHCP and ARP lookups. And the nice thing about this scheme is, since we want to implement this in embedded systems, it's constant time and constant space. So for the lab, we also need a few administrative procedures like the initial registration. Well, you can find the MAC address on your phone in one of the system menus, but it's not very convenient. There's a much more convenient way for the initial registration. Just connect to the lab Wi-Fi and visit a personalized URL, maybe given to you with a QR code, and then the system will automatically record your MAC address. Also, you have to consider phone replacement. People lose phones, replace them by new ones, although the rate is decreasing. Market studies say, however, still phones are replaced. So you can automate the process based on your primary authentication scheme, and maybe have some safeguards if someone is using this more than one time in 3 months, for example, he or she should probably contact the administration. So, conclusion. So MAC addresses are not very safe. Of course, they are not unspoofable, and maybe if you root your phone, you probably can fake them. So we're only proposing this as a secondary method in addition to a strong primary authentication. On the plus side, it's very lightweight, it's easy to use, it's almost nothing to carry. It's you get 7.5 points from 8 on the Bonon UDS framework. It's operating system agnostic. You have no need to maintain a large operating system base. And you might combine it with additional features, like maybe use it on the entrance as well as a secondary method. But this is the point that I missed at one of the on the introduction slide. The system for the Happy Lab system for authentication for running a Fab Lab is mostly on GitHub, and future work would be to include this system into this Fab Lab man project on GitHub. So this is the fast wrap up of the paper, and we probably make it on time for lunch. But questions? Thank you.